Here's a choice. Option A, win $1 million, no strings attached. Option B, gamble and have the chance to win $1 billion. You have a 1 in 500 chance of winning. Which option would you pick? Option A or option B? Most people will, after some thought, pick option A. $1 million is a lot of money, and what would I do with $1 billion? But if we look at the maths, the expected value of option B is actually twice as large. So mathematically, we should pick option B. This difference isn't a flaw in our intuition. It's a flaw in our model. Let's try to fix it. We face choices all the time. Should I buy pizza? Probably. Should you bike in the rain? Probably not. Should you text your crush? I don't know. It quickly becomes fuzzy and philosophical. Mathematics, on the other hand, feels absolute and binary. 1 + 1 = 2. Pi does not equal 7. In this video, we'll venture into the intersection of mathematics and philosophy and try to mathematically model our philosophical choices. Let's consider a simple game. Flip heads to win $10. You have a 50% chance to flip heads and a 50% chance to flip tails. The cost to play is $4. Your choice is to play or not to play. Let's consider that expected value again. The expected value of this game is simply 50% times $0 and 50% times $10. So the expected value is $5. So mathematically, we should play. In this case, our intuition aligns well with the math. This seems like a great game to play. So why doesn't this work for this million versus a risky billion problem? Clearly, the math and our intuition diverge. The crucial insight here is that money does not equal happiness. Or money does not equal utility. Utility is this philosophical term that's a sort of generalized happiness. We can try to model our choices using something called utility functions. So, while $1 billion equals 1,000 times $1 million, the utility $1 billion brings you is not 1,000 times the utility of $1 million. You won't get 1,000 times happier. You've already bought the house and pizza. Probably a better model is something like, the joy you get from going from $1 to $10 is roughly the same as the utility going from 10 to 100 or from 100 to 1,000. You need more and more cash to gain the same amount of extra utility. But our model so far has simply been that the utility of our wealth is the wealth. It's a linear function. This means if we have, for example, $20 to spend, we gain more utility linearly as we add money. And it doesn't matter if we add that money when we're rich or when we're poor. We'll get the equal amount of extra utility. This seems a bit unintuitive. Something that might model this change better is a logarithmic function. It tapers off as the wealth increases. Adding more wealth adds less and less utility. For example, adding $20 when you're relatively poor gives you a lot of utility. But adding it when you're already pretty rich doesn't add that much. Let's test this model. Intuitively, most people pick option A. Let's see what the math says with this utility function. Our expected utility is just the utility of the wealth after the event. So it's our initial wealth plus $1 million. Let's make up an initial wealth and say it's $10,000. If we plug in the utility function and substitute in the values, we get a result of 6.004 utilities. For option B, we have a 1 in 500 chance of getting the utility of our initial wealth plus $1 billion, and 499 out of 500 chance of just being left with our initial wealth. Again, plugging in the values here, we get a utility of 4.01. Comparing the utilities of option A and B, we see that clearly option A is better. So far, this aligns well with our intuition. But what happens if we change the initial wealth? As we increase the initial wealth, we see that the difference between utility shrinks. For initial wealth of $1 billion, option B suddenly provides more utility. Let's investigate this a bit more properly. We'll plot the difference between the expected utility of option A and B as a function of the initial wealth. We get this beautiful looking curve that clearly states that below a certain value, option A is better, but above it, you should pick option B. As we trace that function, we can see that the inflection point is somewhere around $400 million. But we can learn more. There's another beautiful perspective to this curve. We have this expression for the expected utility as a function of initial wealth and added wealth. What we can do is we can invert it, solving for wealth as a function of expected utility and initial wealth. What this means is, given some initial wealth, adding this utility is equivalent to gaining this much money. This is a bit more intuitive than this utility number, since we have a feeling for how much money means in certain contexts. If we plug in the numbers for option A, we see that we just get back the value of $1 million. This makes sense. Adding $1 million guaranteed should feel like getting $1 million. But for option B, we see that the equivalent value is just around $230. That's a lot less. Let's deep dive and make a proper plot. Let's sweep this equivalent value as a function of the initial wealth. For option A, we see that we just get out a constant $1 million of equivalent wealth. And this makes sense. Gaining a guaranteed $1 million should feel like getting $1 million, regardless of your initial wealth. For option B, it gets really interesting though. For small initial wealths, we see that the equivalent value is almost zero. But then, as we pass some inflection point, the value smoothly transitions to be around $2 million. So if we would have to choose now, we would compare the difference between these two options. We see that for low initial wealths, we should pick option A, and for large initial wealths, we should pick option B. The point where this changes, we can see, is again almost $400 million. 397 to be exact. This gives a much more nuanced picture than just the expected value. And what's truly fascinating is that for large initial wealths, the result is the same as the simple expected value. And this also makes sense. If you're a multi-billionaire, this is basically like getting a guaranteed dollar or a 1 in 500 chance of getting 1,000. We are actually faced with questions like this all the time. Should you work in a safe job, making 100K a year? Or start your own company with maybe a 10% chance of success, with the potential of gaining $10 million? The reality is that most people choose the safe job. But imagine if we mitigate some of that risk. A society might choose to provide free healthcare, free education, free childcare, affordable housing, affordable food, etc. A real-world example could be Sweden versus the US. Sweden has exceptionally strong social security. Sweden also has way more billion-dollar companies per capita than the United States. These public policies might be a contributor to that. A utility function like this also makes a strong case for collaboration because it spreads the risk. At the same time, it also explains why the rich get richer. If you already have a lot of money, you can afford to take some risks for higher expected returns. Although I find it beautiful that this simple function can explain so many phenomena, it's not complete. We started with a simple linear function, the expected value, and ended with this logarithmic function. But it doesn't tell the full story. Probably a true utility function depends on way more than just your wealth. For example, it might depend on the wealth of your friends and the people around you. Another factor might be the change of utility over time. Basically, are things getting better or are they getting worse? What do you think is missing? A perfect utility function might not even exist. The best we can hope for is something that models the situations we face adequately well. Thanks for watching.